recording here. This afternoon, we're going to continue our exploration of what can be done with the shell. Before I continue, I didn't get any questions earlier, so hopefully everything was pretty clear and straightforward. Again, just continue to drop questions in the chat if you have any. Otherwise, before we move on, Alexi, who will be helping us this afternoon, drop some information in the chat about how you can use the less command to explore files a little bit more efficiently. One of the things you can do with the less command is you can jump to specific file lines by putting in a plus number and then the G here, which stands for the start of the file. So this is plus 1000 lines from the start of the file to file name here. You can see this will automatically jump to the 1000th line. Also note that because less is interactive, when you bring up the help in less by pressing H, you get a whole heap of information about other key shortcuts you can use. So you can actually search forwards and backwards, you can move forwards and backwards. For example, Z and W here can be moved to used to go forward and backwards one window, or E to go forward and backwards one line. So for example, if we're just using E, see here we're jumping forward one line at a time. W, move back one window, and so forth. But I'll let you explore the help at your own pace and in your own time if you want to learn how to use less to explore files efficiently. Okay, if you didn't get the data that we were looking at previously, the wget command is still in the chat. We'll be using that data again in the following session to look at some other commands that you can use on the command line to pull apart your text data. So the next example is basically going to use a command we haven't seen before, but it allows us to essentially look at how long a file is, and it's called WC. And in this example, we're going to pass it the -L flag and just put in the email file again. What the WC command does is it's basically like an aggregator, so it will perform a number of operations based on whatever flag you pass it. The -L in this case stands for line, so in this instance we're counting the number of lines in the file, which is 542,000, and you'll remember from the less command we could also see 542,000 lines, but we have to open the file to do so. So WC is a neat little tool that can help us do things like that. We can also use WC on multiple files. So remember when we extracted a data set, we had a whole heap of these FASTQ files. Now, we could, for example, type the name for each one of these into the command line, or like tab complete them into the command line after using WC-L. But there's actually a smarter way to do that, and that's using the wildcard operator, which is essentially called a glob. And a glob is basically a directive that tells the shell to expand all of the matching paths as arguments. What does that mean? Well, In short, if we did wc-l and then we did a star.fastq, this glob operator will be taken by the shell and it will look for all files in the specified location where this glob operator is true. So where this glob essentially refers to any set of characters before a .fastq. So that's going to basically return all of these files. In fact, you can test it by just doing ls star.fastq, and here you can see it just matches all of the fastq files. Getting back to our WC, star.fastq. This instance, WC is going to go away and calculate the number of lines in each file individually, and then also give us a total. So here we can see that each file has 20,000 lines for 320,000 lines in total. If we didn't have the .fastq after that glob operator, then what we would actually get is the line count for every file in the current directory, right? So this is going to match all of the files that it can find, and it will also fail on the files that are directories rather than text files. You can also, let's get through some of the exercises here, use multiple wildcards in an expression. So let's, for example, say that we want to match the files that contain this FB string, or this substring FB. We could, of course, count the number of lines in each file individually, but you can also just as easily use a glob operator on either side of an FB. So in this instance, the expression here will look for files that contain FB in any part of the string. If we just had the glob at the front like this, then it would only return the file where the FB was at the end. If we had an FB at the start, then it wouldn't return anything because there are no files that start with the expression FB. So in this instance, if we give the 2 stars here, or the 2 stars to represent the glob operators on either side of the FB, then we count the 2 FB files in this directory. The other thing it can be useful to use globs for is to iterate over a number of files doing other types of operations like copy or move. Now you can't do rename operations with globs because you have to rename each individual file to be unique. But a good example of where this is useful is if we make a directory called fastq. We want to store all of our fastq files in. We can use a glob operator here to move all of the fastq files into the fastq directory. This slash on the end here just indicates that it's going into the directory. And we now have a look at the contents of this folder, this directory. We see that our fastq files are gone. We have a look at the contents of fastq. We can see that it just contains all of our fastq files. So you can see that you can use the glob operator essentially as like a filter on patterns in your file names, which is a really good reason and a nice segue to talk about the fact that you should be mindful of how you name your files. So ideally, you might want to name your files in a logical way that that has some kind of meta information in the file name. So that might be the date, it might be a name of the source of the file or some information that refers to the contents of it. It might refer to the run or the execution run that you have that file associated with. And then also to have meaningful extensions to the files so that you can move files that are related or remove files that you don't need because they have a particular extension. Maybe they're just logs or peripheral information to help you debug your programs after they've run if necessary. There are some good guides on the web to help you understand how to successfully name files. Find the one that I saw earlier. This is quite a good reference deck that talks about how to name files when you're creating them, to help you organize the data and also to help you leverage the way your computer interacts with those file names. So to make it easier for you to filter them, to make it easier for you to glob them, or to utilize the information in other software. Cool. Okay, any sort of questions there about globs? They might be a bit confusing at first. I think if you've used kind of wildcard notation, it should be a little straightforward, or at least intuitive. Definitely not quite as difficult as regex expressions and stuff. Cool. All right. So the next section that we're going to talk about is redirecting output in the shell. So sometimes, or we talked about originally how the shell has this read, evaluate, print loop type scenario, right? This is the paradigm under which it works. And a lot of the time printing to the shell is useful. It gives us back information that we want, and we can interpret it quickly before moving on to the next command, and that's perfectly fine. But there are scenarios where it may be handy to output the print from the shell to a text file rather than displaying it in the shell itself. When we do that, the output is basically stored in the text file, and it's also not returned to the shell, so we don't overpopulate the shell with information. Quick example of that, I introduce another new command now called echo. Echo is a command that takes a string as an argument or a file as an argument and returns the string or file that you pass to it. So to give you an example, let's put in a string here, which is a bit of text by these double quotes. And echo is just going to print that back to us, essentially echo it back to us, right? You can tell pretty much any command line program to output its statements to a file by using what's called a redirect, or in this case, the right arrow or greater than arrow, right? You then have to give it file name, and when we run that, we do not get anything printed back to the shell. However, have a look at what's in that test.txt. We can see that it contains what we expected would be returned from echo based on the previous example. Another example of where you might use a redirect, we got quite a bit of information when we ran wc-l for the whole directory, but we could also, that's my accounts. But we could also redirect that to a file using the same syntax. So again, we've got the command as if we were running it without the redirect, and then we tell it where we want it to output its print returns. It still gives us errors because it wasn't able to do these things, so it tells us what it can't do. But if we now look at that line counts.txt, you can see that we get back just the line counts for the different files in this particular directory. Let's talk a little bit more about why these errors don't end up in the line counts, but they do end up on the screen, and also why, for example, when we run this command just without the redirect, we see everything. And so in Unix, there is essentially a number of what they call pipes or memory buffers where information can be output to by programs when they're run from the shell. So there is the main one, which is stdin. So this is where information is input to a program. Then there's a buffer called stdout. So this stands for standard out, where information is written to the shell. And this is kind of where the print comes back to you. And then the third one is called std or std error. And this is where information is sent that is produced by errors caused by the runtime of your program, right? So when the program tries to do something that it's physically not able to, and the programmer is trying to tell you that there's a problem. Now, which types of information end up in stdout and std is dependent upon what the programmer who created the command line argument decided it should be. But generally, you'll get to kind of know these things, and you can capture the information from stdout and std in different ways. So if we go back up, sorry, I didn't point this out earlier, but if you use your up and down arrows, you can navigate through previous commands that you've typed into the command line. And this can make it easier to fix commands you mistyped or to redo commands you want to do again. So in the instance that you want to redirect the output of stdout, then you just use a single redirect arrow like so. But you can also capture the output of std by using a 2 arrow. So this should be errors.txt. In this instance, we're going to direct the output that goes to std out to one file, and the output that goes to std to a second file, so we can separate the two. And you'll see that we no longer got the error output dumped to our screen. If we have a look at what's in cat.errors.txt, you can see that this now contains the errors associated with running that code. So this can be a useful way of filtering errors out of your output. We could also just output the errors to a file and see the std out by removing the single arrow redirect. And in that case, we get the std out, but not the errors which are dumped to the text file. The final way you might want to interact with these things, these pipes, as they're called, is to output them together. So you want to capture everything into one file as if, you know, the way you view it when you just print it to the shell. And in that instance, you use an ampersand with a redirect arrow. And now if we look at the contents of together.txt, see that it contains the errors. Any questions about redirects or the pipes? Okay. The last thing I'm going to show you about redirects is the use of the append operator. So in all of these instances, when we output, if I go back to the simple one, line counts.txt, if I run this twice, I look at line counts.txt, it still just shows me the output of the most recent run of that command, right? So line counts is overwritten every time I use this redirect operator with line counts as the output destination. I can, in fact, adjust that to be an append operation by using a double redirect, so the double right arrow here. And in that instance, I'll run it again. And if we have a look at line counts, we can see that we've output the process twice. So we have a file that contains what we've run 2 times. And you can continue to append to files as much as you want using this method. Cool. The other nice thing about pipes is that they present an opportunity to chain commands together. So up until this point, we've been running commands with just a single command with a single set of flags and a single set of arguments. But it may be, and it can be useful and powerful to do what we call command chaining, where you redirect the output of one command to the input of a second command, and even continue to redirect beyond that into a third or fourth command. You'll start to see common sort of expressions that people use to do this, but they always contain the vertical line, which is often called the pipe operator. So this is the vertical line or pipe. We're going to introduce another command now called grep, and grep stands for generalized regular expressions or global regular expressions. I can't remember which one. If you start to get into text processing or text file processing in any way, learning regular expressions can save you a ton of time because they are an incredibly powerful syntax that allows you to extract information or to filter information in really efficient and powerful ways. We could probably run a 1 or 2 day course on regular expressions, but for the moment, just know that it is a way of interacting with text using a set of principled rules that tell the program how to find matches or to extract matches of information from text data. The grep command is just grep, and you can pass grep essentially a string that you want to match in the simplest case. In this case, we're just going to look for the string ACT5C. Capitalization is important here, so it's case sensitive. And then we're going to pass it the dmail-all GTF file. If we run that command, what we get back is a ton of data. As you can see, that all contains this ATC5C string. But it's clearly not all the data because we've only got maybe, I don't know, 50 lines here, something like that. Amazingly, even though there were 500,000 plus lines in this file, the script ran more or less instantaneously. So this is a really quick and powerful way to find and extract information that you might be interested in from really large text files. What we can now do using the pipe operator, though, pipe the output of this is essentially a text file, essentially, right? Like this is just a whole heap of lines of text now to head. And remember, head gives us the first 10 lines of a file. But we can also just get the first one. So let's just get the first line that matches this ACT5C string. In that instance, we return just a single line. We can see that it contains ACT5C. We could also see what maybe the first 5 lines with this string match look like. And they're similar. Some numbers are different. Some are mRNA lines, or this 5UTR line, or this exon line. And some are a bit longer with some additional information. But this quickly allows us to kind of get a feel for what might be returned if we started to filter things based on this ACT5C string. We can also see how many lines contain this string using grep piped into WC-L. So in this instance, we're going to find all lines that match ACT5C, send that output to WC, and then count how many lines there were in the output. In this instance, we can find 46 lines containing the ACT5C string. So there's an exercise now. We are here working from this worksheet. And I want you to think if you can work out a way to count the number of files in the FASTQ directory we made earlier using the shell and a combination of perhaps wc-l pipes and another command. Just give you a couple of minutes to think about that. Okay, hopefully you all worked that one out. Let's think about this. We can list all the files in a directory using fastq using ls. So this just returns a list of all the files. In fact, we can redirect the output of ls to text file as well. It'll just give us, so let's redirect this to cat so we can see what it would look like if we put it in a text file, right? Need to pipe it, sorry. In that instance, we just get one line per each record, even though the records are kind of printed, or the files are printed here all punched up to save space in the shell. That means we can also just count the number of files with wc-l, right? So we're just going to pipe to wc-l, and pretty quickly we see that we've got 16 files. Now, the next exercise here asks you to use gzip to turn geneassociation.fb into geneassociation.fb.gz. And then you can use another program that we haven't seen before called zcat that allows you to read compressed files without decompressing them, so you don't have to unzip the file first. But how could you combine zcat with another command to look at just the top few lines of the compressed file? Okay, so hopefully that was pretty straightforward as well. So a quick look. We need to use gzip to zip up our geneassociation.fb file. So we run that, have a look, and we've got a geneassociation.fb GZ. So this is compressed now. In fact, we can have a look at how big it is. Now there. So this is now 1.8 megabytes, and I think it was about 22 or something before. So that's a decent amount of compression. Then we want to have a look at it using Zcat, but I think if we input the whole file, we're going to get this interpretable whole file mess again, which is not useful. So we use Control-C to exit that. So instead of just printing the whole file, we're going to pipe it to something that allows us to look at the top few lines, the head. Maybe we just want the first 5 lines, say. So, in that instance, we can see there's a little bit of a header here to the file. Maybe we can have a look at 15 lines, see if we get any data. All right, so there are 5 header lines, and then the data kind of starts here, and you can see this is all tabulated information that we could then input into another program or code. Very good. All right, that kind of ends this section. We've had a look at a few different things, including some new commands like WC and Zcat and gzip. There's also been a bit of a look at globs, which was the star operator or the wildcard. We've talked a little bit about how the different pipes work in the shell, particularly std out and std and how you can redirect the print part of your commands to files or to other commands using the pipe operator. Does anyone have any questions about how those operators work or any of the content we just covered? Maybe you want to see something a little bit different, or you're not quite sure how this all fits together. Hopefully when we get to some more concrete examples, you'll see that you can use this essentially to do a lot of on-machine post-processing or pre-processing of your data using the cluster that wouldn't be possible using your local machine, for example. All right, if not, we might continue then onto the next section. We were scheduled for a break, but we've done just over 40 minutes, so I think we might do a bit more and then maybe break halfway through the next section, which is on scripts, variables, and loops. Cool. So what do we mean by a script? Essentially, when referring to the shell specifically, a script is a text file which contains a recipe or sequence of instructions which we want the computer to execute. And in the simplest sense, we can either be repeating a task, or we can be repeating a sequence of tasks on a particular input. So that input could be a particular type of file, or a set of files, or it could be a folder location, or just about anything you can think of that sort of exists on your computer that you can access through the command line. The reason we write scripts is because it can be quite tedious, obviously, to input commands repeatedly and then to have to take outputs and input them into another command, and then to do that for 100 or 1,000 files, is just an incredibly tedious sort of task. So scripts are there to make our life easier. They're also there to eliminate errors. And in a way, they also capture our thinking, because when we write scripts, we do a lot of research and thinking about how we want to process something. And the script kind of captures that knowledge, so that when we come back 6 months later and we rerun some experiments and we want to run the same processing again, we don't have to go, oh, what did I actually do in the post-processing step to get all my information out. So the scripts are useful ways of simplifying and speeding up tasks, as well as capturing processes that you might be running regularly in relations to your data, right? So let's look at how we might write a script. We're going to start with a script that we're going to call demo.sh. So let's create a file with Nano, our text editor, remember. So a script is just a text file that contains some instructions. And by convention, we usually put a .sh extension on shell scripts. So this just tells us that it's a program that we want to be able to run with our shell. Remember, extensions don't really mean anything in Linux, but they're useful as indicators to us as humans what files are needed for or what they're used for. So we just hit enter and we get a fresh file called demo.sh. So we can see that up here at the top. Because we're using bash, we can add a directive called a shebang, which is a hash bang here. And we want it to point at the location of the bash executable. And this is almost always /bin/bash. And this is essentially directing the shell to the program that will be used to interpret this file. Sometimes you'll see other things written at the top here, like /bin/python or /bin/sh or csh. And these all refer to different shells or software that can interpret text files as scripts, and Python is one of those. Another one, for example, might be Perl, if anyone's familiar with Perl, or what's another good one? Maybe awk, which is a text processing command line utility. So let's, very basic, an echo statement into our command. The example here has the text our script worked. So we're going to echo, or we expect our script to echo us back a string called our script worked. We save that out with Control-O, enter, and then exit back Control-X. And we can run this command in a couple of ways. We can call bash like this, and it will ignore the shebang at the top. In this case, it will just run the text file using bash, and we get our script works. We can also just run, we can try to run demo.sh, but we get an error. And that is that the command is not found. That's because the location we're in is not on the path that bash goes to look for programs. So whenever you put a command here at the front, it's going to be looking for a program in that path. We can force it to look at a particular file, putting a dot, so the dot, remember, is this location, then a /, so here, and demo.sh. So this will force it to look in the current directory for the file we're trying to run. And now we get a different error, permission denied. And by default in Linux, you cannot execute every file. So you have to make files executable. And this is a nice segue into talking about file permissions. So let's bring up the long list of files in this folder and talk about what these permissions mean at the front here. Where's our file? There, demo.sh. So this is demo.sh here, right? We know that the one right out the front refers to whether it's a directory or a file. So this one's a file, fine. And then we have 3 banks of 3 different letters. And they're always RWX, RWX. Oh, this is this. Why is that this? Can't remember. RWX. So it's usually just RWX. If you see a blank or a hyphen here, that means that that option is not available. And the 3 banks refer to the user who owns the file, the group, and everyone else. So in this instance, everyone can read the file. Only the user can write to the file. And no one, so this last column here is the X, which refers to execution. So no one can execute the file. And that's the same for this demo.sh. In this instance, then, we need to change the permissions of this demo.sh so that it can be executed. For example, directories, I think, can be executed so you can get into them, but it doesn't mean you can run it as a program. And the way you do that is through a command called chmod. So change mode, right? So we want to change the mode of the file. So let's bring back all the information. So we have no execution permissions at the moment, but we can add execution permissions to a file for the current user by using the +x and the file name. So we go chmod +x demo.sh. Now if we relist the files, it changes it for everyone. So now everyone, this user, the group, and everyone else can execute this file. We can actually be more explicit about these permissions, and we can prevent reading or writing of different groups, reading or writing of specific users, and also the ability to execute. But I don't know if we cover that in this particular part of the lesson. For now, know that if we want to create a file that's executable, we need to use this +x. If we go back to the command that we tried to run before, /demo.sh, now that it's been set to executable, we can run it. So what's the difference here between the situation where I ran bash demo.sh versus the ./demo.sh? I guess the difference here is that if you want to use the shebang notation at the top of the file, that was the this shebang to indicate which program should run the file, then you need to make the file itself executable. Whereas if we just call bash explicitly, then we can just call the file itself. All right, other things that you can do with scripts. In bash syntax, a hash at the start of the line indicates a comment. So if we comment out our echo statement here, save that, exit, and rerun the script, no longer get any output. And that's because the comment lines are ignored by the bash shell interpreter. We remove the comment, save the file, exit, and our script prints again. So comments can be used to either make notes in your files or your scripts, which is a good thing to do, or to prevent lines from being executed. What else can we do? We can define variables. So variables are defined by, usually by convention as uppercase, with an equals, and then you can have something that is full statement after that. So in this case, because we've got spaces, we need to put some quotes here. This means that our variable will contain the string, this is our variable. So our variable var will contain the string, this is our variable. It's important that you have no spaces around this equal sign in bash. To then see what's in our variable, we can use echo, but to tell bash that we're talking about a variable rather than a string, because if we just put var and we get var back, we need to use dollar in front of the variable name. And so we get back, this is our variable. So how do we use that in the script? We go back to our demo.sh. Let's comment out that line because we don't need it. And create some comments here. So set our variable to the name of GT file. Let's create a variable called file, and this is the dmel-all-r6.19.gtf file. And going back to what we learned earlier, we want to call wc-l to get the line count on the file. And the way we're going to do that is just run wc-l. And remember, we need to use the dollar here to reference the variable name, so we can use $. So remember, you can follow along with all of this. This is all available in the documentation currently. Here, I'm going to post something in the chat for you, a link to the current documentation. So if we write out our new script and then we exit, and we run our script, we are expecting line counts for or just the file dmel-all-r6. If we run that, we see we get the line count, which is great. So it's recognized the variable name. However, let's think about this, right? if you wanted to run this particular program, every time you wanted to run it for a different file, you would have to go into the editor, change the file name here, which you can't actually see or autocomplete with Nano, and then exit and run the program. So ideally, we would want to be able to pass some arguments of our own to the word count or the line count, essentially, that point at a particular file. Fortunately, Bash has a nice way of doing that. That is just using the dollar number or dollar integer notation. The integer refers to the position that the argument you pass has. Right? We'll talk a little bit about that soon. Let's save this out. So we're going to call wc-l $1. So saving that out, we exit. Now when we call .demo.sh, if we don't give it an argument, nothing happens because we didn't give it the $1 argument. It's just waiting for us to input it. So let's Control-C out of that. Bring demo.sh, and then put in our dmel-all-r6 file. So in this instance, the *1 here, sorry, the $1 refers to the first positional argument, or the first argument not associated with a flag, right? Is that clear to everyone? Is there any issues with the idea of like the position of the argument on the command line and how that links to the dollar integer notation in the script itself? I think we will get to, I don't know if we do. Let's quickly do another example. We add a second argument to this command line. Let's go $2, right? So we're going to run two commands. First one's going to operate on the first argument, and the second one's going to operate on the second argument. So if I save that and exit, I've got two different DML files here. And so one unique protein isoforms. So this would be, because it's the first, this will be $1, and this will be $2. And if I run this, then I get the return for both WCL operations that were in my script. Hopefully that's clear. Right. Another thing you might want to do when you're running a script is you might want to output the contents of a command to a variable. So in the same way that we were piping commands into one another, you can essentially save the output of a command to a variable and then use it later as an input to another variable in your script. So this might be useful if you need to do multiple steps prior to doing one sort of combined step, or if you need to capture some kind of state within your script before you finish. So the way that's done, let's do this from itself, is that you can assign commands to a variable. So you can execute a command on this side. But I'll tell you now that this kind of syntax won't actually work because this needs to be a singular expression. So with the spaces here, it will be interpreted badly by bash. So he doesn't understand that this is a flag of a command that needs to be executed. The way to get around that is to, again, use the dollar notation, but to wrap the command that you want to execute in some parentheses here. So now when we run this, ls-l is executed. The output is captured within this variable, and then that temporary variable is output into the variable named test. And we can see what that looks like, again, by using echo here, the test variable. So we get all of that output, albeit without the line returns to make it look pretty. All right. Any questions about variables before we move on to loops? Nope. Okay. So let's create a new file called loop.sh. And we're going to put our shebang here at the top, points to the bash. If you ever have problems with these shebangs, you can come back to the command line and use a command called which. If we put bash in here as the argument to which, it will tell us the location of that command. In fact, you can use this for any command. So we could look at, say, where is now installed, and you can see that's installed to another location. Or grep is installed here, for example. So this can be a useful command to sort of find out where stuff is located. Let's go back to editing our loop.sh. And the way loops are written in bash is we have a for, and then you have a variable that you're going to assign your iterable to. And then you have a list, which is just a space-separated list of variables or objects that you want to iterate over. In this case, these will all be interpreted as strings. Then you do a loop. So you have to have this kind of do operator because bash uses these kind of keywords, do and the ending one done as closure, opening and closures for this loop, rather than brackets like you might have in we do, and we're going to just echo the variable var. So we've got a $sign because it's a variable, whereas here this is like an assignment operation, so we don't need the $sign. And we're going to finish with a done. So this tells bash that this is the end of the loop. This indentation actually isn't important. You could leave this like this and it would work perfectly fine. I just like to indent because it allows you to sort of see the for loop block a little bit easier when you're writing bigger lots of code. So I'm going to save that out, exit. If we want to use our /execution method, then we need to chmod loop.sh to make it executable. Use /loop.sh to execute it. See, we get each one of those variables from the input iterated over. So we get first printed or echoed, then second, then third. Pretty straightforward, yeah? let's move on to something that's a little bit more useful than printing just arbitrary strings. Let's create a variable called files, as its input or assignment takes the contents of ls. So in this case, ls will be all the files in the location where we execute this script. Then we can say for var in $files, remember we need the dollar because we're trying to reference a variable here. Let's do the same thing. Let's just echo the name of the file, right? So this is a slightly pointless script because it's just going to take the output of ls and print it again. But for the sake of demonstration, let's see what this is. So in this instance, we get a new line return because echo by default returns a new line, and we're outputting each of the files that are located in this current directory. If I hit ls, you'll see that we have the same files, albeit with the sort of condensed printing that you don't get when using echo. What's another thing we could do? Maybe instead of iterating over all files, we could just iterate over all of the unzipped files in the current directory. So remember, this is the glob operator. It's just going to match all .gz files. And this will be basically executed in the current directory. So we'll only find gz files where we run the script. If I run /loop.sh here, it will just show me all of the gz files now. All right, over to you guys. Got a couple of exercises here to get us to the end of the section. I'm going to give you 2 to 3 minutes for each exercise, and then we'll go through each one. The first one here is to cd into the fastq directory we created earlier, and to write a script that has a loop to print off the name and the top 4 lines of every file that it iterates over. So I'll give you 3 or 4 minutes to do that one maybe. Remember, if you want to see the syntax that we have for for loops, you can go to the last link in the chat segment, and that'll take you to this page where you can see things like this, for example. Right, coming back in 4 or 5 minutes, so about 2:44. Okay, welcome back everyone. Hopefully you've had a bit of a good break and a chance to digest what we've just been talking about. I haven't seen any questions, so I'm just going to run through this first example. We've then got a couple of other examples for you to try some of the ideas from today, and then we'll wrap things up. That'll sort of complete the session for today's workshop. Done really well, made it through a lot of content today, a lot of ideas, so hopefully you've all learned something and found this useful. Anyway, so the question was, can we print the name of every file and the top 4 lines of every file in the FASTQ directory? So let's bring up our shell and go into FASTQ, and let's create a new file called, print top 4 .shell. Create that using nano, and start with our shebang /bin/bash, so we can execute this without calling bash directly. And then we want to loop through all the files that are FASTQ files. So for file in glob.fastq, because they all end in FASTQ, right? So just filter them quickly using this FASTQ. Glob.fastq filter. Then we want to start the for loop with a do. We wanted the file name, so we just want to echo the file variable, right? Because that'll just be the name here from this glob operation, which expands to find all the matching files. And if we want to see the top 4 lines, we can use our head command. So within the loop, we can put a head. Get the first 4 lines, we have the -n flag, which we used a few times already. We'll just set that to 4. And then we need to pass it the file as well. Go ahead and close our loop with done. Cut that out. That's it. Set the script to be executable. And all things being well, if we print that, we'll get each file name and 4 lines. Very good. Did anyone have any trouble with that or questions about how that was done? The example itself is here in the documentation, so you can find a solution available if you are still struggling with that. But there was a second aim here that I didn't look at. Is there a way to run the loop on FASTQ files ending in _1.fastq? Let's go back to our list of files. Right, so it looks like there's like for each one of these files, there's an _1 and an _2. Yes, we could just go back into script and change the wildcard to match the _1 as well as the .fastq at the end of each file name. So now when we run this one, we just get _1s here printed out rather than the _2s and 1s that we had previously. All right, please, if that's not clear, let me know. Otherwise, Let's move on to the next exercise, concatenating variables. So concatenating variables together is quite easy to do so. Add whatever you want to concatenate to the beginning or end of the shell variable after enclosing it in braces characters. So, right, so we can create a complex string by putting the variable that we're interested in braces, and then putting the rest of the string after that. So in this example, they have, if you set a variable file to be stuff.txt, and then you ran echo with the variable inside braces, and then put .example on the end, the output would look like this. So the exercise is, can you write a script that prints off the name of every file in a directory with .processed added to it? So we need to write a loop for every file and then use this knowledge that we've just learned to append .processed to the end of every file name. I will give you guys let's say until 1:15 to have a look at that one. All right, I've had quite a few people indicate they're finished, but I haven't seen much movement on the bar. Does anyone else want a little bit more time to finish this before I complete the exercise here on the screen? Just let me know in the chat. It's fine. We've still got another minute or two. All right, not getting any no's, so I'm going to take that as implicit yes. All right, so in this example, we just wanted to modify the file names to add the .processed suffix to everything. So I'm going to use the same, let me just close this, FastQ code that I wrote last time. Let's the print top 4 to a file called processed.sh. In fact, here, when you copy a file like this, it retains the permissions, so we won't need to do the chmod stuff to the processed file. But if we go into process.h, for each of the .fastq files, we don't need to echo the file name, but we do want to, oh wait, we want to echo the file name, but we don't want to see what's in the head. But we want to change the file name so that it is processed. The way we do that is to stick file in braces like this, and then we can put here on the end. The braces here just stop Bash from assuming that the whole thing is one variable name. So they kind of help the bash interpreter understand that this is a variable, and then we're just concatenating some string text to the front. So now let's save that, run it. We can see that we get a dot processed on the end. What are some other interesting things that we might like to do in this kind of situation? Maybe fast queue is something we want to preserve, and we want to put the process front. Should be able to be processed either on the fly here, so see if this works or not. Echo is a nice way of testing things. You can see if it doesn't work. I think we can process as a prefix rather than a suffix. There's also methods to strip the suffix or the file might do this after we come back. All right. Okay, back to the exercises. Okay, final exercise for the day. This one talks a little bit about managing permissions for users, groups, and everybody else. So remember that for a single user or group or all other users of the computer, you can set a file or folder to have read, write, and execute permissions. And in the world of Unix, those permissions are actually represented by a number. So read is represented by the number 4, write by the number 2, and execute by the number 1. And what this means is that if you combine or you sum these numbers together, you can get a numerical representation that tells you about every possible combination of read, write, or execute for a given user or group or everyone else. So for example, if we just wanted a file to be executable, not readable or writable, then its permission would have the value 1. If we wanted it to be readable and executable, then its permission value would have the value 4 plus 1, so 5. And if we wanted it to be readable, writable, and executable, then we have to add everything together, which gives us 7. So when you set permissions for something, you can specify a number between 0 for no permissions and 7 for all permissions for each of the 3 different groups. So the first number here refers to the user, the second number refers to the group, and the third number refers to everyone else. So you'll often see, if you're doing any Googling or trying to find out how to do something, people writing chmod and then a 3-digit number. And that 3-digit number tells you about the permissions for that file that they're trying to set, and it tells you about the permissions for each of the 3 groups that we talked about. So in this example, this would be the first digit, this would be the second digit, and then this would be the third digit. because we've got RW, we would have an R, which is a 4, plus a W, which is a 2, so that gives us 6, which is unique for that set. Then we have just an R, so this would be a 4, and this would be just an R as well, so this is 4. So the overall permissions for this file would be 6, 4, 4. If we look at a slightly different example, let's take this print top 4 shell file, which we wrote. In this instance, we've got full permissions for the user. So this is 4 plus 2 plus 1, which is 7. Then for the group, which is this column here, the TA076, that's our project group. That's the group that the file belongs to. So any users who are part of this group are able to do these things to the file. They can read and execute it. So that's going to be 4 plus 1, so this is 5. So we've got a 7 followed by 5. And then for everyone else, it's the same. They're also read and execute, so another 5. So this will be 7, 5, 5. Okay, so hopefully that's relatively clear. You'll find that these numbers have been chosen in a way that creates unique values for any of the combinations. So there's 7 different combinations because there's 3 values. And from that, let's look at the exercise itself. Let's make an example file and give everyone permissions to do everything with it. So this is the example file. Remember we talked about touch earlier. That just creates a text file. And then if we have a look at the permissions on that, we'll see that they're somewhat limited. But if we chmod 777 that example file, then everyone will have read, write, execute permissions. We can check that with another ls-l afterwards. So knowing that, how would we give ourselves permissions to do everything with a file, but allow no one else to do anything with it? So what 3 digits do we need to use with chmod to protect a file for just us? Hopefully this shouldn't take more than a couple of minutes. So I'll check back with you soon. Try it out in the shell using this kind of formula. And then we'll run through the results before finishing up. Okay, hopefully that was pretty straightforward. Let's quickly run through an example here. We're just going to use our process.sh. So if I want to restrict that so that no one else can view, modify, or execute it, then I need to give myself full permissions, which is 7, and give everyone else no permissions, which would be 0, 0, 0. So I do process.sh here. And have a look at that. You can see that I have now given myself full permissions, and everyone else has no permissions. If I want to give read permissions back to people, then I need to set these to 4. So read was 4. Now if I have a look, you can see that we've returned to a state where read permissions exist for other people. I don't want anyone outside the group to be able to read it, then I would set this to 0, so 7.0. No one else beyond the group, TA076, can read it. And if I want TA076 to be able to read but not execute, then execution is 1. So read plus execution is 5. And there we go. Now it's limited to the group, and other members of my project can read and execute the code but not edit it. And because I have the W here, I can also edit it. Maybe if you make something that you don't want to be changed by yourself, even you would even consider 550. And you could read and execute it, but never modify it unintentionally. So this would prevent you, for example, from overriding something unintentionally. Okay, so that sums up the session today. If anyone has any questions, I can stick around for a few minutes after the session ends. Otherwise, I'll see you all back here again tomorrow at 9:30 for the next half of the workshop, where we'll be logging on to ARCHER2 and learning how to interact with the scheduler system and to run some parallel code and to think about how we can make best use of the resources that are available to us. So thanks for joining in today, and I'll see you all tomorrow.